Okay, I can hear the music playing again. So does that mean I've accidentally pressed the wrong button? That's entirely possible. Okay, good morning and welcome to Physics with Keith. It is Saturday at 10 o'clock in the morning, which means it's time for our free online physics tuition session. And I've been playing around with some of the settings and some of the software to see if I can make things work a little bit better. I think I've got sound coming out of my computer, and that's what I can hear. Right, okay, I need to pause this. There we go, that's better. Right, sorry about that. I was trying to work out why I could hear things echoing twice. Hopefully you didn't hear that echo, but I certainly did my end. Okay, anyway, we're going to finish off electromagnetism today. Good morning, Freya. Good morning, Wombatcom. Yes, we're going to finish off electromagnetism today, which, if you recall, was requested a few weeks ago. 3 weeks ago, and then it's over to you. Hello, Lex. It's over to you to see what it is you want to work on after that. I haven't had any requests come through or anything like that, so really this is going to be just finishing this off. And if you have any questions while we're going through things, yeah, you need to ask. You need to get involved and go ahead and ask. So we're going to switch across to there. Did that work? Yes, it worked. Okay, as I say, I've changed some of these settings. You probably won't see any difference on your side, but I can certainly see differences on my side. I'll pop that there. So the last thing we looked at last week before we ran out of time was this little simulation here. We didn't really get a chance to look at this simulation, but I just flashed it on the screen and said, oh, we ran out of time. So we're going to start with this. This simulation is a virtual physics lab simulation. I'm not affiliated with them in any way whatsoever. I get nothing for promoting them, but they have very kindly given me permission to use their simulations in these tutorials as long as I mention the Virtual Physics Lab website and the good work of Dr. John Nunn, who created all these simulations. So, this is where we finished off with, and we were looking at electromagnetism. What we've got here on the left is a coil of wire. What we've got here on the right is a coil of wire. I don't think I have audio. Lex, that's a problem, because according to my computer, I do have audio. Oh, no. Freya, Wombatcom, do you mind confirming that I have audio? Interesting. Wombatcom can hear. Someone called Ty. Oh, that's someone new. Hello, Ty. Welcome. You can hear as well. Maybe your end, Lex. I'm sorry. Yeah, Freya seems okay. I think it's your end. Certainly none of the settings I fiddled with have affected that. Okay, so here we've got our dynamo, and we've got this bar magnet in the middle, and it doesn't really matter if the red end is the North Pole or the South Pole at the moment, as long as we know they're two different poles. And we've got our field lines, which we know come out of a North Pole into a South Pole. But we've not bothered drawing arrows because we're not actually that bothered with this. And on the right-hand side here, we've got, although you can't see it, probably on your screen, there is a light bulb. And you can barely see it. If I get this magnet rotating around here, then as the magnet rotates, the field, the number of these field lines that passes through this coil changes. And if you watch, it seems to be very, very jittery, but if you watch, the number of field lines is increasing, and now it's decreasing. And I can speed this thing up. I can get this thing rotating a bit faster. So the number of field lines is increasing, then decreasing, and then increasing the opposite direction, then decreasing, then increasing, then decreasing, then increasing in the opposite direction, then decreasing, and so on. And that's what's happening in this simulation. And I can make it go even faster and even faster and even faster. Now, what's happening here is the coil is seeing this changing magnetic field. And the universe is not a big fan of change. Newton's first law of inertia for mechanics, for motion, tells us that things don't just spontaneously start moving in the universe. You have to have unbalanced forces to cause acceleration. Similarly, things don't spontaneously stop moving in the universe. You have to have unbalanced forces to produce an acceleration in the opposite direction to motion. So that's your mechanics. But here we're looking at electromagnetics, and we've got this sort of electromagnetic inertia as well. So this coil sees an increasing magnetic field, and it doesn't like it. And so it tries to stop that increasing magnetic field by producing its own magnetic field that opposes the change that caused it. We call that Faraday Lenses Law. So as this, that's Lenses Law actually. So as this magnetic field is changing in this coil, the coil objects to it and produces its own magnetic field. Now, how does a coil have a magnetic field? Well, we looked at this a few weeks ago. We go all the way back to here, all the way back to here, where we had a single wire with a current passing through it, having a magnetic field around it. But if I were to loop that wire around like this, then you can see in this diagram, I use my right hand grip rule. At each point on this wire, where the thumb of my right hand indicates the direction of the current, the fingers show me the direction that magnetic field is. So we did this, I think it was 2 weeks ago. But if you look in the middle of this loop of wire, the field is always going into the screen. And feel free to get your hands out, your right hand out, and start practicing this and having a look. As the current is going in the direction of the thumb, at each point, the field, the magnetic field, is going in to the middle of this loop of wire and out at the edges. And if I were to take multiple loops, multiple turns, then we'd end up with a magnetic field that adds up. Each loop produces its own field as the current passes through it, and these effects add up to produce a larger magnetic field. And one way I could make that magnetic field even stronger is by putting a bit of soft iron in the middle. Remember, iron is one of those magnetic metals, ferromagnetic metal, and if I put iron in the middle, it reinforces the magnetic field by becoming magnetized in a direction that means it produces its own magnetic field that reinforces the magnetic field where the iron has been put. So I put the iron into this into this, what we call a solenoid, this coil of wire, and the magnetic field that the coil of wire produces is now greater. It's now a stronger magnet, electromagnet. So I go back to here. Oops, where was I? Ah, right, no, I'm looking at the simulation. If I go back to here, I can place a piece of iron into the middle of these coils. I'm just going to look at the left-hand coil today. It doesn't matter, but I'm just going to look at the left-hand one. So if I place a bit of iron in the middle, I've now made the magnetic field that is produced or induced by both of these coils. I've made that now stronger magnetic field. It can now generate a stronger magnetic field. And what does that do to this current? Well, you can see what this does. The light bulb, you can now start to see it flashing. Now, I'm going to ask you a quick question. I'm going to want you to type your answer. When is the light bulb brightest? How would you describe the time, the instant in time when the light bulb is brightest? Use as few words as you can, so you're not taking a long time typing. But go ahead and type your answer to that. When does it appear as though the light bulb is brightest? How would you describe it? Well done, Lex. That's good to hear. Ted, that's a really, really good answer. More magnetic fields in the coil, yeah. More magnetic, yeah. Really good answer. But actually, I can tell you that you're wrong. And let me show you why. Right now, there's loads of magnetic field lines going through that coil. So the magnetic pole is closest to the coil of wire, which is what Wombat.com. How bright is the bulb? So, I mean, how bright is the bulb? I reckon you can answer that. Is it a bright bulb? Is it a dark bulb? How bright is the bulb right now? It's off. It's dark. It's very, very dark. Very, very dark. So it's not about the field lines. There's something more tricky going on. No. It wasn't rhetorical. That was a genuine question. My apologies. I should have made that clearer. Yeah, there's no light at all coming out here. Something more tricky going on. So what's going on? I reckon you can give me a better answer now. Especially if you're... Yeah, I had fun with that, Freya. I spent far too long playing around making soundboards. I've got loads of them lined up for when it's appropriate for me to use them. So, and they're all royalty-free, of course. I made sure of that. Now, Wombat.com, I know that you are doing A-level physics. So this is going to be good for you. For everyone else, you don't have to know the mathematics of what's going on here, but you do have to be able to explain in words why the light bulb is brightest when it's brightest. Yeah, see, Wombat.com, that's still not really an answer that's going to get you the mark. It's more... Okay, it's more to do with how quickly the magnetic field is changing. As the magnet passes around this this region, I know, I'm just being silly. As the magnet passes around this end here, the number of field lines that pass through the magnet is changing most rapidly. And you can see that. I mean, if I make this go a bit slower so we can really track what's going on. Right now, there's no field lines. Then loads of field lines, then no field lines. We need to go a bit slower. Let's get this really, really slow. Really, really slow so we can really see what's going on. So let's count every Mississippi. So 1 Mississippi. There's no change in field lines. 1 Mississippi. Oh, there's one change. 1 Mississippi. I've just added about 10 field lines in that Mississippi. 1 Mississippi. 2 field lines. 1 Mississippi. 1 field line. 1 Mississippi. No field lines have changed. 1 Mississippi. 1 field line has changed. 1 Mississippi. 4 field lines have changed. 1 Mississippi. Okay, you get the point I'm trying to make. There it is. Well done, Wombat.com. The greater rate of change of field lines. So the greater rate of change of what we call magnetic flux linkage for A-level students, or for GCSE students, you could just get away with saying the rate of change of magnetic field. That's enough for you. But for A-level students, the rate of change of magnetic flux linkage, well, it's directly proportional to the what we call EMF, or potential difference across this coil, or the voltage across this coil. And if you've got a bigger voltage across the coil, you've got more current through the coil. And if you've got more current through the coil has a bigger magnetic field strength of its own. It's a stronger magnet, bigger what we call flux density in this coil. So when we have the largest rate of change of flux linkage, in other words, when the number of field lines crossing through that coil per second is changing most rapidly, then we have the biggest current induced in that coil to produce the biggest magnetic field to try to oppose that change. But it's got to be changing for the universe to try to oppose it by producing this magnetic field in the coil, inducing this magnetic field in the coil by inducing the current in the coil that would produce that magnetic field. Now, when I teach this, because it all seems a little bit circular, a little bit confusing, what caused what? You know, what's the primary reason why this happened? What's the order of these operations where one thing led to the next, led to the next? Actually, the universe doesn't quite work that way. It all happens together. But I usually sort of describe it in terms of the universe deciding it doesn't like this change and then imposing its will upon this coil in order to make current happen. And it's all a lot of nonsense, but it does it does help students to see, okay, maximum rate of change of flux linkage, therefore maximum EMF induced in this across this coil, therefore maximum current through the coil, therefore maximum magnetic field produced by the coil, but the direction of that magnetic field that the coil produces is opposing the change in magnetic field that caused it. It's a complicated idea. It's probably the most complicated idea, one of the most complicated ideas that you'll see in A-level physics. So if you're a GCSE student watching this and you are baffled by what you've just heard, don't be downhearted by that. It is weird. It is hard. So we're going to go through this really slowly and show you what's going on. And I'm going to have to try and pause it at certain points. So at this point here, let's say this is the South Pole. The blue is the South Pole. So At this point here, are the field lines going in to the magnet or out of the magnet? Are the field lines going into the magnet or out of the magnet on the left over here? If this is a south pole. Into the magnet or out of the magnet? It's a south pole, so the field lines are going into the magnet. Well done to Wombat.com. In if it's a south pole. Field lines go out of a north pole into a south pole. So the field lines are going in here. This coil is seeing an increasing amount of field pointing to the right. So this coil does not like seeing an increasing amount of field pointing towards the right. It wants to reduce the amount of field that's pointing towards the right because it's currently increasing in that direction. So it pushes back, producing its own field to the left. And so the current is induced in the coil in a direction that means that the field that the coil produces is to the left. Now, in this region here, so remember we're rotating anti-clockwise, the field lines are still going, these are the field lines that the bar magnet has, are still going to the right, but the number of field lines to the right passing through that coil is decreasing. And the coil does not want to see a decreasing amount of field going to the right, so it produces its own magnetic field now, but in the direction to the right, to try to reinforce that decreasing magnetic field. It doesn't want it to decrease. It got used to it being how high it was. It doesn't want it to change. And so what that means is we have a current induced in the opposite direction now to try to keep that field there. Okay. So then we fast forward to this point here. The red part is the north pole. So in general, are the field lines going out here to the left or are they going in here to the right? So out to the left or in to the right? What do you reckon of this bar magnet? Where the red is a north pole today. Going outwards, which is to the left. Yeah, outwards. So they're all going out to the left. Are they increasing the number of field lines or decreasing the number of field lines? Increasing or decreasing the number of field lines? Yep, increasing the number of field lines going to the left. So what does the coil do? If it sees an increasing amount of field going to the left, what does it do? Well, not a force, Ted. Everything else you said was correct, but it produces a magnetic field of its own to the right. Yeah. So Wombat.com, it's worth actually saying the direction as well, because I was being, because I was talking about the direction being to the left increasing, we would have to say, okay, so the coil produces its own field to the right to oppose this. Yeah, okay, so then what happens in this part? Remember, this is rotating anti-clockwise, so what happens at this point? What happens at this point now? We're rotating anti-clockwise. I'm giving you no more clues. I've scaffolded your answers up to now, and I'm taking more and more scaffolding away. Just looking at the coil on the left. Magnet's rotating anti-clockwise. The red part here is a north pole. Okay, so there were certain things that you said that were absolutely correct. Certain things you said that were absolutely correct there, but there were a few areas where we can improve it, Wombat.com. Clockwise magnetic field to reinforce the change. We're just talking about left and right, Lex, not so much clockwise, anti-clockwise at the moment. I don't know how this coil is wired up to know whether the current is clockwise or anti-clockwise. And you were talking about magnetic field. So, Wombat.com, let's pick yours apart for a second. Decreasing rate of change of flux linkage. Right, well, it is decreasing rate of change of flux linkage. That is correct. But the flux is decreasing in the direction to the left. So the flux is going into the coil, but it's going to the left. And it's decreasing, which means that the coil doesn't like this, which is what you said. The coil produces a magnetic field to the left. Yes, that's absolutely correct. And then you said to try to attract the magnet. I mean, that will attract the magnet, but I'm not sure if I'd say that's the reason why it happens. But it will attract the magnet. But I wouldn't add that bit into the answer. I would say it's to oppose the change that induced it. And that's the terminology I would use at GCSE level as well as at A level. Opposes, it's not so much the motion of the magnet, it's opposing the change in flux linkage. Okay, in this case, the change in flux linkage is caused by a rotating magnet. But it's the change in flux linkage that induces the current in the coil to produce its own magnetic field to oppose that change. Okay, now that is weird. It's difficult. It's conceptually difficult. And you can always watch this back again if there are stages there that you want a little bit more help with. And you can ask questions. You can ask questions. Of course, you're allowed to. I encourage you to ask questions. But just very quickly, that's the principle of how a transformer operates. So here's a transformer. And on our transformer, we have a primary side and a secondary side. And we've got this soft iron core, which is laminated and yada, 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 which I haven't got time to talk about now. We put a current through this coil. And the secondary coil on the right-hand side is not electrically connected to the left-hand coil, to the primary coil. Those two coils are not electrically connected to each other. And yet, electrical energy from over here can be transferred to over here. And so the question is, how does that happen? Well, it uses this magnetic field as a conduit to exchange that energy. However, it only works if you've got an alternating current in the primary coil. We need an alternating current in the primary coil because if we've got a changing current in this coil, it produces a changing magnetic field. The iron, which becomes magnetized, means that magnetic field is sort of forced to go through this secondary coil here. It would rather go through the iron core because the iron becomes magnetized, reinforcing the field in that direction. So this secondary coil here will see downwards the field if the left-hand coil, the primary coil, produces an upwards field, and vice versa. The field goes in a big circle. And if the primary current is changing, then the magnetic field that is produced by that primary coil is changing, which means that the magnetic field that this secondary coil sees is changing. And of course we know that coils don't like seeing changing magnetic fields. They oppose that change by producing a magnetic field of their own in a direction that opposes that change. And they do that by having a current induced in them. So on this particular picture, you can see there's more turns on the coil on the left than there are on the right. It turns out, if we go all the way back to here, it turns out that if I have more turns on my coil, with the same current going around it, the magnetic field is stronger. That's the way it is. We add up the effects of these magnetic fields. And there is that quantity that I mentioned the name of that doesn't really come up in GCSE level called magnetic flux linkage. And the magnetic flux linkage is a way of quantifying the amount of field lines that this thing, this coil, interacts with. And the more turns you've got on the coil, the more chances there are that the coil will interact with this field. That's a bad way of describing it. But if I've only got one turn on my coil and I've got 10 field lines going through it, then that has half the same effect as if I have 2 turns on my coil. Field lines go through the first turn and then they go through the second turn. And so we've doubled the effect with having 2 turns. And you have 4 turns, we double it again. And 8 turns, we double it again, and so on. So magnetic flux linkage depends on how many turns are in our coil. The more turns we have, the greater the flux linkage for a given flux density. And there's fewer turns on the right-hand coil in this particular transformer, which means that for the same flux density, there's less flux linkage on the right-hand coil. If there's less flux linkage, there's less rate of change of flux linkage. I'm going to go definitely into A level now. So if you're watching this and you're doing GCSE level and you're lost, stand by because there's going to be a quickfire round in a second. Oh yes, a quickfire round. You'll enjoy it. Or you won't. It doesn't matter. It's happening either way. So if I were to draw a graph, which I'm hoping this is going to come out clearly enough, like this. A nice graph where on the x-axis I've got time, and over here I've got the amount of flux, and we use the Greek letter phi for flux, or I could even use a capital Phi for flux linkage. Then because I have an AC current in the primary coil, I have an AC current induced in the secondary coil. It's going to look a bit like this. It's going to be some sort of sinusoidally varying. Oh, that was terrible. Oh, disaster. Look at that. Oh, no. What a terrible sinusoid. This is supposed to be a cosine. I'm going to stop. I'm going to quit while I'm ahead. That was awful. What I hope you can see is that the maximum rate of change happens here and here. Rate of change is a gradient on a graph of something plotted against time. But if I were to take this and I were to increase the maximum, what happens to the gradient? It increases. I can prove it to you. I can take this line, which I badly sketched. I can paste another version of it. I can change the colour of it so we can see what we're doing a little bit more clearly. Pick a colour. Let's go with red. No, that was the circle I changed the colour of. Let's try that one more time. Pick a colour. Let's make it red. There we go. And let's have a smaller maximum flux linkage. And you can see, right, I mean, you can see in this region here, smaller maximum flux linkage means for smaller rate of change, maximum rate of change of flux linkage. So the root mean squared EMF that's induced is going to be smaller if you've got a smaller maximum flux linkage, which you will have if you've got fewer turns on your coil. Going back to GCSE now, so if you'd switched off because you thought, gosh, that was confusing, come back to me. GCSE level, we use this equation, and at A level as well. VP is the voltage across this primary coil. This one here. The voltage between one wire and the next. VS is the voltage across the secondary coil. And what we'll talk about here is sort of maximum voltage or root mean squared voltage. It doesn't matter, it works either way. NP is the number of turns on the primary coil. NS is the number of turns on the secondary coil. And we can use this equation to determine what the voltage is on, for example, the secondary coil if we know the voltage on the primary coil and the number of turns on each. We can do all that sort of calculation. And the last equation I'm going to show you before we do the quickfire round is this one. Electric power is voltage multiplied by current. And if we assume that our transformer doesn't lose any energy, so there's no wasted energy, then every watt of power that I put into the primary side should come out the secondary side. Every joule per second I put in one side should come out the other. Which means the voltage multiplied by the current on the primary side is going to equal the voltage multiplied by the current on the secondary side. Okay, I think it is now time. Let's see if I can get this to work. Yep, I think it's time for the quickfire round. Okay, quickfire round. So these are all very, very short questions. Just hit your answer. It doesn't matter if you're wrong or right. Let's go. First one. I'm just having so much fun, Freya. I don't know why. I'm just messing around with it. Okay, let's go. What do you think the answer is? A, B, C, or D? You might need a calculator. You might be able to do it in your head. Keep trying, keep trying. Okay, the voltage has been halved. If the voltage has been halved, then... Hang on, have I got the wrong answer written down? Has it all gone horribly wrong? I'm saying wrong. I've just checked. I think I've got the wrong answer written down. Oh no, it's all gone wrong. Potential difference on the primary is 20. On the secondary, it's 10. So the voltage has been halved, which means the current has to have been doubled. So the answer should have been C, which is what Freya originally said. My apologies. Okay, let's hope I've got the answers right for the next one. Oh, I know why, because I've started on question 9. Come on, you muppet. Right, there we go. Read the answer to the wrong one. I wasn't calling you lot muppets, I was calling me the muppet. A, B, C, or D? Oh, I've hit the wrong button. Okay, I'm not going to make a game show host anytime soon. Yes, the answer is B. Okay, next one. First finger field is in, second finger is current, which is in the right-hand direction, so the force is up. The force is up. The crosses are in, that's right. Crosses indicate in. Okay, that's what we're learning. We're learning, we're learning. Here we go, next one. Doesn't matter if you're right or wrong. Oh, lots of outwards was correct. It was incorrect. It's outwards. First finger field. Second finger is the current, so it's going in. Oh yes, lots of people saying in. That's very good. Okay, next. Oh no, it's out. What am I talking about? I'm talking absolute nonsense. First finger field. Second finger current. It's in. It is in. First finger field. Second finger. First finger field. Force is down. It's out. My goodness me, I must be tired or something. It's out. All those people saying in are incorrect. It was out. Oh, I've spent so much time playing with the silly little toys, I didn't actually put any time into the physics. Next one. Might need a calculator for this one. Oh, I know, but I don't like doing it. But thank you. You're too kind. At least I recognise them. This is the thing. If you realise you make a mistake, because you do, you go, ooh, that doesn't seem quite right. You go back and you have another look. It is D. It is D. Congratulations. Okay, next. I agree, Wombatcom, but I'm supposed to already know. Next question now, Lex. Next question now. Freya, it's the next question now. I've changed it. You'll give me the answer to the previous question. It is indeed A. Why is it going bling at the same time? It shouldn't be doing that. That's better. I might not be doing it your end. Yes, it is A. A. Okay, next question. A, B, C, or D? Vote, vote, vote. It is A. Well done, Lex. It is A. A is the correct answer. Next. Probably won't need a calculator for this one. It's not C. I hope. It's B. B. Well done. And the last one. B. Well done, Ted. It is B indeed. Very good. But we didn't need a calculator for that one either. B. Yes. Well done. B. Good. Okay. And that was the quickfire round. Let's see if I can get this right. So, there is obviously an awful lot more that we could talk about with electromagnetism. As a topic, it is vast. At A level, we would spend 4 weeks, maybe even 6 weeks, working just on electromagnetism. At GCSE level, we'd probably spend 3, maybe 4 weeks working on electromagnetism at that level. And it is a tricky concept. So in 3 half-hour sessions to try to get through it has been a bit of a challenge, and I obviously missed an awful lot of stuff out. If there are parts when you're going through questions, exam questions are the best way to go with this, and obviously I can't put those on this video because I don't own the copyright to them. But if you go through exam questions, look up websites like Physics and Maths Tutor, which have free resources for all different exam boards, sorted by topic. Grab those exam questions, work your way through them, and then if there are any way you're not sure about, you can bounce that to me through Facebook Messenger, and then I can talk about them in the future. Now, I'm open to suggestions. What is it, the next topic you want me to look at? And if there's something that you in particular want to look at, drop me a message either on Facebook Messenger, just put it on Facebook as a comment onto one of my many posts, or you can even mention it here now. Have I mentioned? I haven't covered electricity yet. No, I haven't, Wombatcom. And actually, that's a topic I really do like going through. Kirchhoff's laws in particular, I think, are absolutely critical. So if there's anyone else that says yes, electricity is a topic I want to go through, or even if they're not, and that's the only suggestion we've got, then yeah, we'll make it electricity. And I've got some great question generators I've written, which I can send to you. If you're interested, drop me a message on Facebook Messenger, and I can send you that. Well, I imagine they will do Wombatcom, but if they're not, they'll send me a message. Yeah, Freya's fine with it. It's a good topic. It's a tricky topic as well. Did you do it in the summer school? I think I did, Ted, but again, that was very, very small, very short sort of section that we did in the summer school, trying to cram it into 1 week, whereas electricity we could do over a few weeks, and it would really be worth doing. So, electricity, what we'll do, again, just like with all the other topics, we can actually start at GCSE level, but if we do it properly at GCSE level, and I mean Kirchhoff's laws, make sure you understand that, then when we get onto these sort of A-level questions, GCSE students will be able to follow it no problem, and the A-level students would definitely benefit from it as well. There really isn't any difference as long as you learn it properly first time. Right, thank you very much everyone for tuning in. I'm sorry I've had some technical difficulties near the start with this new setup, but I think I got there in the end. And I'm sorry that when I was running through the testing, I'd left it on the last question and yet looked on my list of answers at the first answer. I should have trusted everyone else before I trusted myself. Have a lovely week. Stay safe. Drop me your questions, please do. Encourage other people to get involved. And I will, yeah, good. I'm going to see what else I can do next time. But in the meantime, thank you very much. Stay safe, and I'll see you again.